All right. What if I don't want Wendy's? No, I'm just kidding. Then I'm up the creek, huh? All right. So on a typical clear day, the atmospheric electric field points downward and has a magnitude of approximately 100 Newton per Coulomb. Okay, so eventually you learn that Newton per Coulomb and volt per meter are the same. So every 1 meter, there's 100 volts. That's an electric field pointing downwards. Compare the gravitational and electric force on a small dust particle. Okay, so this calculation is the following. Okay, grab hold of a bunch of dust, throw it in the air. So you have these particles in the air, and the greater the downward force, the greater will be the terminal velocity. Well, I mean, the greater the terminal velocity, faster it settles down. So here's an example again. You guys understand? All right, I throw this dust particle in air, they'll settle down faster. I throw this same thing in water, it settled down slower. The terminal velocity is slower. Okay, so if there are charged particles and if the electric field is pointing down and if the particles gather negative charge somehow, now the terminal velocity, they'll feel an upward force and so they'll settle down slower. Okay. And that's a problem. So on a typical clear day, the atmospheric electric field points downward and has a magnitude of approximately 100 Newton per Coulomb. Compare the gravitational and electric force on a small dust particle of mass 2 times 10 to the minus 15 grams that carries a single electron charge. What is the acceleration of the dust particle? Okay. So here's the dust particle, here is mg. The electric field is downwards and it carries a negative charge, so the force, the electric force is in that direction. Okay. And the magnitude of the electric force is Q times E. And it carries a single electron, so it's E times. Okay. So what is the acceleration? So the net force on it is the mass times acceleration. And let's say, I don't know which one is greater, but let's say this is greater than that. So we'll assume this direction is positive. It doesn't matter. mg minus Fe equal to m times a. Okay, and what if that was greater? Then the acceleration will come out negative, meaning the acceleration is upward. Instead of falling down, the particle is accelerating upward. Okay. So the acceleration is mg minus Fe divided by . Okay. So let's put in the numbers now. Let me first calculate this. EE. The charge of the electron is 1.6 times 10 to the minus 19. And all we need is magnitudes now because I've already put in the direction. 100 Newton per Coulomb divided by the mass, which is 2 times 10 to the minus 15. Oops. 10 to the minus 18 kg. Okay, let's take care of powers of 10. This is 10 minus 19, 10 minus, that's 10 minus 1. That kills 1, so that's 10. 16 divided by 2, which is, oh, I don't even need a calculator. So minus 8 meters per second square. This is G is 9.8 meters per second square minus 8 per. Okay, so this will accelerate downwards, the particle. Yeah. Now, of course, if it had 2 charges, 2 electrons, then it would accelerate upward. That would become 16, and then it would accelerate upwards. Okay. So the acceleration is 9.81 minus 8 meters per second square. 1.81 meters per second square downwards. All right.